Hello, how's it going? Thanks for coming to Free GMAT Prep Hour today. It's good to have you here. My mouse is trying to show you an entire preview of the slideshow. So we will be doing a lesson focused on a single topic today. Maybe you already got to see it. I was hoping it would be somewhat of a surprise, but my mouse had other plans. Cool. Let me go ahead and get this thing started. Remember that the chat box is open, and I'm going to be asking for responses in chat. So please let me know when you have questions, when you have thoughts or answers to the questions that I'm going to show up on the screen. And let's just go ahead and get started. So a reminder before we dive into the lesson that you have some other free options for prep through us. You can come to a trial GMAT class. Please come to session 1 in person if you're in a city where we offer classes, or online, and you can log in from wherever as long as you have a decent internet connection. Or check out our GMAT program called GMAT Interact, and you can kind of test that out for free, get a little preview of what Interact's all about. Pretty cool resource. I direct my course students to Interact a lot to follow up on lessons from class or to review some stuff. So reminder that you have some other free options for prep. Cool, let's just go ahead and dive into a problem, and I think the lesson will emerge from that. So I'll give you a couple minutes on the clock to tackle this monster, and I'll check in a few minutes. If you have an answer, go ahead and hold on to it for now. Don't publicize it. Just a heads up, that's been 1 minute. Keep working. All right, that's been about 2 minutes. I'll give you a little bit longer to think about your answer choice, if you have one. And let me launch a poll here so I can get a sense for what we're thinking. Go ahead and give me your best answer choice in the poll. So far, I have 5 votes in, and I have 1 vote for each answer. That's awesome. All right, so if you are not sure, this would be the perfect opportunity to guess. Remember, we are going to encounter some brutal problems on this exam. We need to not waste our entire life on a single problem. We have to go ahead and submit an answer, and so I'm going to ask you to do that now. Give me your best guess. All right, this is so widely spread that of the answers that have come in, no answer has more than 30% of the votes. So it's that widely spread. Cool. I'm going to go ahead and end things there. I think if I show the results of this, it won't show up on YouTube. But just so you know, only one answer has 30% or more of the votes, and every answer choice has a vote. So I put this problem on here because it's so awful. And so what I'm going to try to do today is we're going to back away from this problem. We are going to level up on some other problems, equip our toolbox, and then revisit this problem. And we will hope to give it a better shot. All right, we saw the dragon, we got scared of the dragon. Now we have to go, practice our sword fighting. So when we see the dragon again, we have a better shot. Cool. So we will see this problem again. It will come back before the end of the lesson. Hold on to your horses. Let's go take a look at a different one. All right, so this is a data sufficiency problem. I want to give you 2 minutes to solve this one, and hold on to your answer choices when you've got it figured out. That's been 1 minute. All right, we are just passing 2 minutes. So go ahead and take another 15 seconds, try to come up with an answer, and then I'll ask for it in a moment. Cool, everyone go ahead and type your answer into chat and send it in to me so I know what we're thinking. And you're welcome to send it in to just me, or you can send it into everybody if you have that option. Another problem where the first 3 answers I've got are all different. This is good stuff. All right, so I will say now I've gotten all the answer choices except E, so you guys think that this one is solvable. Let's start from the top here. I have a bunch of people who have chosen answers A or D. Okay, and so if you're picking answers A or D in data sufficiency, what you are saying is that statement 1 is sufficient on its own, that knowing length AC and that it's 8. Radical 3 is going to be sufficient. I want you, if you chose answer A or D, tell me in chat why you think statement 1 is sufficient. So why is statement 1 sufficient? And I think about half the people gave me answer A or D. Actually, more than half. Kind of quiet. Okay, so a question came in. Yeah, because the triangle is equilateral. So John, how do you know that? How do you know the triangle is equilateral? Well, I mean, so I guess something on the page says it's equilateral, like this does. But remember, we're looking just at statement 1. Okay, quite a couple other ideas coming in. To draw a circle touching all sides, the triangle has to be equilateral, maybe. Or the circle's radius is consistent and fits in the triangle, so it's equilateral. Well, let me see. Like, what if I drew? Okay, so Jesse, I'm going to come back to that in a sec. Let me try to draw another circle here. This is about as good as it's going to get. Let's say I have another length that looks like this. Okay, I'm trying to make this drawing like relatively faithful to what I have here. I think this looks pretty good. It looks like I could create maybe something close to an equilateral triangle out of this. My question is, how do we know that this length is perfectly centered on the circle? Like if it were moved here, I think I should be able to draw another triangle that like holds the circle. That was actually pretty good. Surprised I could do that. So we can see that if a circle is inscribed in a triangle, the triangle doesn't have to be equilateral. I could make an infinite number of triangles that inscribe a circle. And so this is one of these common kind of traps, all right? You have to be very careful about these in data sufficiency. Just because it looks, in this case, like an equilateral triangle doesn't mean that it is. And we'll see that if it's just a little bit off being an equilateral triangle, then you can't figure out the perimeter from knowing one side. So that is going to be a trap. Statement 1 is not sufficient. I could create another triangle. Let me see here. Yeah, that one's kind of mean, but that's how it goes. Some of these problems are pretty mean. I will say this problem's not nearly as mean as the first one. The first one is extremely mean. But yeah, you could start seeing how you could start really warping these lengths. Looks like I needed to do that a little bit better. But pretty soon it becomes obvious that knowing one side is not going to be enough. There, that one's closer. Yeah, so now that clearly the perimeter is going to be greater than 3 times 8 root 3. So that would be kind of how you can prove it. So big takeaway, don't assume sizes and shape relationships. We always want to infer them, never to assume. Again, you can think of the GMAT as ultimately a big exercise in what you can infer without assuming. So whenever we make an assumption, we have to be very, very careful or aware of that. So we're going to say statement 1 is not sufficient, and that is going to rule out answers A and D. Bummer. Cool. Hopefully we learned something like that. Are the pictures there for reference and not to scale? You don't assume things are to scale all the time, especially in data sufficiency. In problem solving, sometimes we have to allow for, some leeway there. Like, I think there's even like a disclaimer at the beginning of the quant section, like all lines that appear straight are straight. In problem solving, you have to be able to get to a right answer. And so, there can't be like little wiggle room. There can't be any ambiguity there. But in data sufficiency, there is room for more ambiguity because we want to know, like, are you sure you can figure this out, right? must you be able to figure this out, not could it be true, okay? Yeah, so again, like they can give you a shape like this and it kind of looks like an equilateral triangle, and I'll be very honest, like when I created it, I tried to make it an equilateral triangle, but just because it looks like one doesn't mean it is one. And that should like kind of, it should inform you then when you move to statement 2, and statement 2 tells you, oh yeah, all of the angles are equal, which means this is an equilateral triangle. And so if you assumed it was before, now that you know it is, we should be able to back up and be like, oh, maybe I'm not supposed to assume that. So if you now look at statements 1 and 2 combined, I know we're supposed to look at statement 2 by itself, but like, let's just go look at statements 1 and 2 combined. If you know the length of AC is 8√3 and you know the angles of the triangle are all the same, then you know ABC is equilateral. And then you know all the sides are equal. And then you know, oh, the perimeter must equal 3 times 8√3. And so clearly combined, they're going to be sufficient, okay? But we have to be kind of careful there, right? So what we've done is we've looked at statement 1, we've looked at statement 2, and clearly combined, they're sufficient, right? This is the recipe for a trap answer. This is called the C trap. Okay, so it was good that no one picked answer E, because we clearly can solve this. Okay, and it's very clear that when you have both statements 1 and 2, you can figure out what the perimeter is like this. But that begs the question, why is the circle here? Right, because if you just look at statements 1 and 2, like the circle might as well not be here. So why are they telling you anything about the circle? Okay. So let's pause for a moment, and I want to determine what is the utility of this circle information? Why are they giving us the circle information? If you have an idea, let me know in the chat box. So if you're given any measurement of the circle, maybe we can just go ahead and write that down, right? Circle. If you're given any measurement of the circle, you can figure out any other one, as long as the initial measurement's not just an angle. Okay, so if you know the angle, the area is 16 pi, and we know the radius is 4. And we know the diameter is 8. And we know the circumference is 8 pi. Okay, so Faye, you wrote in something about using sine, cosine, and tangent functions. You don't need to use any of the trig functions on the GMAT. I mean, you could, but you never need to, okay? So if you're thinking that you need to use some more advanced math, you want to kind of rethink what we're missing. Yeah, it's a relief when you know you don't have to do those, right? Used to know all my like cosecant, cotangent, special angles, and that was just long gone, thankfully. So what we know is we're given something about the circle, and the circle's area is 16 pi, and from that we can figure everything else out. All right, so that means from the center of the circle, we have a radius of 4. John, I need you to rethink that. I think you've leapt to a conclusion there. If you know one measurement about the circle, you know everything else. The circle is a very special shape. And there are a couple other special shapes that are like this. Actually, technically there's an infinite number, but there's one kind of category of shape that are similar to the circle in that if you know one measurement, you know the rest. So what other shapes are like that? Well, a square is like that, right? If you know the perimeter of a square, you can figure out the sides of the square. You can figure out the area of the square. You can figure out the diagonal of a square. From one measurement, everything else is fully determined. And an equilateral triangle is also like that, all right? All the regular polygons have that property. If you know one measurement, you know the rest. And so if you know the distance from the center of the triangle, which is the center of the circle here, to the kind of its its midpoint on a side, and you know that it's an equilateral triangle, you should then be able to figure out everything else, okay? And here is kind of like how it would work. If you know that this is 4, then you can use this to figure out some more lengths. This would be a 30, 60, 90 triangle. And we know it's 30, 60, 90 because this length comes straight down, creates a 90-degree angle here because it's tangent to the circle. And this angle is bisected. If it's an equilateral triangle, it's 60, 60, 60. So if we cut it in half on our way to the center, that'll be 30 degrees. And a 30, 60, 90 triangle has certain side ratios. Now, you don't actually need to know the side ratios here. You just need to know that if you know a single length of this triangle, you can figure out everything else. This would be 4 rad 3. And that means this entire side is 8 rad 3. And then you know it's equilateral from statement 2, so you can figure out that the perimeter is 3 times this, okay? So there are some kind of really important things happening in this problem. I would say first takeaway is don't assume, right? Don't assume, infer. Another important takeaway is knowing the shapes, where if you know one measurement, you know the rest. And whenever you have a tough geometry problem where there's more than one shape, you will want to really consider what is the relationship of those shapes. And here, the circle and the equilateral triangle share the exact same center. And that means if you know one measurement of the circle, you actually can know one measurement of the triangle, and you can connect the dots all the way through, okay? So this is, oh, not a cross out. This is answer B. Yeah, so Karen, you can figure out 4 root 3. It's based on just knowing a couple properties of special triangles. So I'll just kind of quickly diagram the special properties of a 30, 60, 90 triangle. I would derive it from a 60, 60, 60 triangle, an equilateral triangle, okay? So what you can do here is if you know that all of these angles are 60, 60, 60, we can split the triangle in half. Let me go get a different color. We can split this triangle in half. Boom. Sometimes the fancy mathematicians call it dropping a perpendicular. Yes, we'll drop a perpendicular down here. That creates a 90-degree angle there. And now this is 30 degrees because I split it. So if this initial side length were 2x, this would have been 2x. This side length would have been 2x because it's equilateral. That means this side length is x now to go halfway across. And through the Pythagorean theorem, you could figure out that in this side ratios, where the hypotenuse is double the shortest leg, this is always going to be a 30, 60, 90 triangle because of what we just did. We just split this in half. And that means through the Pythagorean theorem, this will have to be x root 3. So the shortest leg to the longer leg is always in a factor of root 3. And that actually means this hypotenuse here would be 8 to the center. You know it's 30, 60, 90 in this triangle because statement 2 tells you the angles are all the same. So you're told that ABC is equilateral. And then to the center of the circle would bisect all of the angles, depending on which angle you started on. Yeah. Yeah, interesting topics. There's a learning curve with geometry for sure. I don't want to use today to go into like every single geometry rule, right? You're going to have to memorize some of like the area formulas and things like that on your own. But just kind of big principles, right? I'm interested in taking away these big principles. So remember, in geometry, don't assume, infer, right? It looks like an equilateral triangle, but we don't know that until we get to statement 2, okay? Because if you do think it looks like an equilateral triangle, well, if you think it looks like an equilateral triangle at the beginning, then actually you don't need the statements at all to solve this. I mean, if you know that the radius is 4, you can actually figure out everything else without the statements. So that would be another kind of signal that we've assumed something. For special shapes, so circles and all the regular polygons, if you know one measurement, you know everything else. And actually you can consider the circle a regular polygon with infinite sides. It's kind of an interesting way to think of a circle. And then if you have multiple shapes, you really need to consider what they share. Those are like the points of interest or the areas of interest in tougher geometry problems where multiple shapes tend to kind of come together or overlap or share a point. Are there readings in GMAT Interact? I don't know. They might go over some of the special right triangle properties in Interact. I would just say, look, the only two triangles that you really need to know are the 45-40-90 triangle and the 30-60-90 triangle. I would just memorize the side ratios associated with these triangles. It's a good flashcard material. All right, let's go on to the next problem. Next problem. Give you a couple minutes to think through this one. That's been about a minute. That's been about 2 minutes. Take a little bit more time and try to settle on an answer here. If you have one, go ahead and send it in to me in the chat box. Stephen, tell me how you got that answer. As you're typing that out, we'll go ahead and get started. Yeah, so if you have an answer, go ahead and let me know. I haven't gotten too many. I'd like to know a little bit more about what we're thinking. All right, so, okay, so Stephen, I actually like what you're saying there. I like the first move is to diagram the triangle on a plane and then solve for the area. Guys, this is gonna be too hard to think about, all right, without visualizing it. So my recommendation is going to be to draw it out. Now, really nice thing about the yellow pad they give you at the exam center, and we have these yellow pads, like if you are in our classes, we've given you one of these. But the yellow pads are gridded, so it actually is really, really nice for drawing out things on a coordinate plane, which of course are gridded. So what I would do is I would just draw this out and kind of visualize this triangle a little better. Let's go ahead and put these points in here. 2, 6 should be here, -4, -1, and then 3, -4. There we are. Now let's just go ahead and like connect the dots and make this triangle. Let's figure out the area of this triangle. So what kind of options do we have now? Okay, we've drawn our beautiful triangle on our really nice coordinate plane here. And now how do we solve for the area? And John, you have an idea maybe as well. Maybe you can let me know. Sharon, or Sharon, I like your suggestion. Although we'll have to adjust one of those words a little bit. So we've got an area, perfect. We've got an area of a rectangle minus 3 triangles. What rectangle? Well, it's not actually highlighted on here yet, but one way to kind of figure out the area of a tough shape is to figure out the area of a larger shape and whittle away until we get to the desired original area. And so I really like this move that Sharon's suggesting. Let's go ahead and draw this rectangle around a rectangle that completely covers the triangle. And then we'll get rid of the other triangles that we don't want. And the nice thing about those other triangles we don't want is that they're all right triangles. So it's pretty easy to calculate their area. Okay. So what is the area of this rectangle? Well, it spans 7 this way, and it spans, this is 6 above the x-axis, is 4 below, so it spans 10. So the rectangle has an area of 70. Let's go ahead and chop away the other pieces. Let's get rid of this big part first. So this triangle here has a span of 6. And it looks like a height of 6, 7. So its area is going to be 1/2 6 times 7. So I'm going to subtract 1/2 6 times 7. Cool. Let's go ahead and take care of this triangle at the bottom. Remember, area is 1/2 base times height. So I'm going to get rid of this triangle's area. 1/2, well, base looks like it's 7 across, from -4 on the x to +3 on the x, 7 across. And the height is 3. And finally, we have to get rid of this little sliver. It has a base of 1. And a height of, it's got the same height as the rectangle, right? From 6 above the axis to 4 below. That's a height of 10. So let's figure out what these are. Well, 1/2 6 times 7, that's 3 times 7. That's 21. 7 times 3 is 21. Half of that is 10.5. And 1/2 1 times 10 should be 5. So I've got 70 for my overall area. I'm going to take away this hunk, which is, this big chunk is 21. That'll give me 49 left. I'm going to now hack away this part. That was an area of 10.5. So now I'm down to 38.5. And now I have to get rid of this little sliver. 38.5 minus that little sliver's area of 5 should be 33.5. We answer C. Yeah, if you chose answer D, likely what you did is you created some kind of rectangle and said, oh, I remember that a triangle's half of a rectangle's area, right? It's 1/2 base times height. So the base and the height, 7 and 10, half of that would be 35. Not quite here. That would be true if our triangle looked a little different. Let me see. If this orange triangle, assuming this is orange, this orange triangle would have an area of 35. Because it does have a base of 7 and a height of 10. But the one that's actually there doesn't quite. It's hard to figure out the base and the height. Remember, base and height have to be perpendicular to one another. And so it's hard to find 2 measurements of this triangle that are going to be perpendicular to one another because it's been kind of skewed and moved around. So the better way, I would say, is to find the box's area and cut out the extra pieces. Yeah. Cool. Let me pause here and see if there are any questions about that method. Why would it be hard to estimate on this problem? Right, like, okay, the box is 70. This is, I don't know, about half of it. Oh, all of these are like about half of 70. So that's gonna be a little tough to do. Oh boy. Sharon, the other formula. Now, there is a way to solve this through a method, and you don't see this method ever taught on the GMAT. Uh, but it's used on, like, you know, middle school and high school math competitions. It's called coordinate bashing. Yeah, I don't think you need to know what that is ever. It's interesting that it works, but you never need to do that on the GMAT. Can you show how to solve using the Pythagorean theorem? I actually don't know how I would solve this using the Pythagorean theorem, because Pythagorean theorem helps me find lengths of right triangles, and I'm not even like given a right triangle here. This initial triangle is not a right triangle, so I'm not sure how I would use the Pythagorean theorem to aid me. Yeah, Pythagorean theorem is more reserved for using for finding side lengths of right triangles, I would say. And I don't really care about side lengths here, and the triangle's not right, so I don't think we have the ingredients for using it. Yeah. Okay, cool. All right, let's move on from here. Let's go ahead and add a couple more things to the takeaway list. So on geometry problems, generally a good idea to draw them out, or if they've already given you a shape, to redraw it. Okay, so a good move. And on the coordinate plane, this is especially useful. Okay. And then if you have a kind of an ugly looking area, one thing to do is like consider getting rid of the other stuff instead of directly solving for the really hard area. Like figure out the areas of like 3 easier pieces, which is kind of what we did. Cool. All right, on to the next one. Here's your next problem. So many shapes. A lot of shapes today. All right, that's been just over a minute. It's been 2 minutes. Give you a little more time. Cool. So speaking of this idea of drawing out or redrawing, here's kind of a way to use the yellow pad at the exam center to help you draw a circle. Okay. So what I've got here is I've got just, a small grid, and on this grid, I'm going to try to draw a reasonable circle. All right. I'm not a good artist, but I think if I can do this, so can you. All right, maybe I can draw a circle. And here's how I'm going to do it. I'm going to choose 5 as my radius. Here are kind of my north, south, east, and west points of my circle. And the point of using 5 as my radius is actually, it came in chat a little while ago. John suggested it. A 3, 4, 5 triangle is a nice right triangle. And so one way to create another, 3 squared plus 4 squared equals 5 squared. And so one way to create more kind of positions that are 5 away from my center are to create these 3, 4, 5 triangles, or 3, 4, 5 triangles. So these 2 points will be 5 away. And I could do it kind of in the other quadrants. 3, 4, 5. 3, 4, 5. And so I should be able to kind of now better kind of guide myself around the circle. I need these dots to help me trace. So again, it doesn't have to be perfect, but actually the more to scale or the more accurately you draw a shape, the better you can kind of estimate lengths and areas. So yeah, then we could add some more stuff. I can't remember exactly what this looked like, but it was, I don't know, something like this. Okay, so I'll go ahead and clean that up and bring the original back. Okay, so I had some suggestions in chat of how to proceed through this. Gui, you said you use a 30, 60, 90 triangle. Quick question, how do you know that this is a right triangle and it's not like 30, 61, 89? Or 30, 80, or yeah, 30, 80, 70? How do you know? Cool, so this just has to be one of the rules that you might want to know. If you have a central angle in a circle, and here we have one, so call this 180 degrees because it's on a line. A central angle is always double the inscribed angle that opens up the same arch, okay? So central angle means it goes through the center of the circle. If that angle is 180 degrees, then it means that line is the diameter. And it means any inscribed angle that opens up the same arch would be a 90-degree angle. Cool. So that's great. Yeah, this is definitely a 30, 60, 90 triangle. Now, what do we use with that? Like, that's great to know. How do we use it? Well, again, if it tells you the circumference of a circle, you can figure out everything else. Okay, if the circumference equals 6 pi root 3, and that's the same as 2 pi times the radius, and you could say, oh, 6 root 3 equals double the radius, and then 3 root 3 equals the radius. So like this might be useful information. So this distance here is 3 root 3. And that means the hypotenuse of this right triangle is 6 root 3. And then you have to remember your side ratios for the 30, 60, 90 triangle. And actually, I'd say even if you don't remember your side ratios for this type of triangle, we're not out of luck, okay? But if you know your ratios, it's gonna be a lot easier. The hypotenuse is always double the short leg, so this is gonna be a 3 root 3. And the short leg is across from the smallest angle, right? Think about this skinny angle. The shortest or the smallest angle opens up the smallest side. The largest angle opens up the largest side, okay? So the hypotenuse will be double the shortest leg, and then the ratio from short leg to the longer of the two legs is in a 1 to rad 3 relationship. So this would be 3 root 3 times root 3. Root 3 times root 3 is another 3. And that's 9. That would be answer D. So I would say knowing all these ratios and the relationships is really good. I don't think it's 100% necessary here, okay? Let's think about how we can estimate the length of B to C, okay? Estimate the length of B to C. So let's think about how much this is. 6 pi rad 3. What is that about? Well, John, how much is 6 times pi? Think about that. So we need to know that pi is, it's a little more than 3.14. Okay, there's some other important irrational numbers to kind of know how to estimate. All right, so root 3 is one of them. I'd say root 2 is another one, your tiny roots. Root 2 is about 1.4, 1.41 something. And root 3 is about 1.7. I think it's 1.73 something. So like take a look at what 6 pi root 3 is. Like it's 6 times something a little more than 3. So maybe that's like about, again, we're kind of loose, but 19 or 20. And then times root 3. So what's 19 or 20 times something that's like 1.7? I don't know, it's like more than 30, but maybe less than 35. I don't know, we'll say it's like 33. Okay, we're estimating, okay? But we know is the circumference is about 33. Cool, like, well, how could we try to estimate BC from that? Like if the circumference is 33, then maybe like half the circumference is like 16, 17. So like this arch is like 16, 17. And that means like, I guess a quarter of the circle would be half of 16 or 17. So like 8. Avinash, if you got a question, go ahead and hit me in the chat box. Yeah. And so if this length is like 8-ish, think about how long BC is. Like if you had a string here and you pulled it tight, would it reach B from C? I don't know, it would get pretty close. So the answer is probably kind of close to 8-ish. And I think D is really the only one that's like kind of close to 8-ish. Like, let's think about that. What's 3 divided by root 2? Think about that. 3 divided by root 2. 3 divided by 1.4? I don't know. 1.4 goes into 3 like about 2 times. That's way too small. 3. That's way too short, right? I'm looking for something 2 or 3 times as big. What's 3 root 3? It's good to have these kind of estimations on hand. 3 times something less than 2 is less than 6. This is about 5. It seems like it's going to come up a little short. 9 looks about right. What's 9 root 3? It's more than 1.5 times 9. Should be 13.5, but less than double, less than 18. I don't know, between 13 and a half and 18, I don't know, 15-ish? That seems too long. 15 is like gonna almost go around the whole half circle. And so only answer D is in range, okay? So estimating here is a great option. By the way, like what is root 2 doing in here? Root 2, when do we see root 2's in geometry? When does root 2 show up? Yeah, Jay, nice. Like you see root 2's in the 45, 45, 90 ratios. And we're dealing with the other triangle here, the other special right triangle. So root 2 is not going to have a place. We use pi's for curves, circles, and we use root 2's for 45, 45, 90s. And root 3's, as we've seen already, root 3's are at play for 30, 60, 90s. Yeah, so answer A is just like, really shouldn't be here. Cool. All right, let's go ahead and add a couple things to the list here. A couple more takeaways. I already drew the circle out. Yeah, whenever you see root 2, like you're on notice for 44, 40, 45, 45, 90 triangles. Whenever you see root 3, you're on notice for dealing with 30, 60, 90 triangles, and vice versa. Right? If you're given information about 45, 45, 90 triangles, like there's a really good chance root 2 is going to pop up. Okay. And then pi, like what are the circumstances where you encounter pi? We think of pi as being an essential number in geometry for circles. And again, we solve that problem two ways, right? We can solve it the textbook way. I'd love for you to know how to do it. I'd also love for you to be flexible enough to know that you don't have to do it that way. And we can kind of just estimate lengths. Yes, the more accurately we can draw some of these shapes, the more closely, the better we can estimate relative lengths, relative areas, and things like that. All right. We've tackled 3 problems, I think of, different difficulties. That last problem, by the way, the one with the one we just did, is from our advanced quant book. Yeah, good book. This one is one of the advanced quant problems from one of the workout sets at the back of the book. If you have a quant score that's in the upper 40s, I would say like above 47, the advanced quant book is a really, really good resource. Really good problems, good strategies. I like it a lot. Cool, all right, so we've tackled a few problems. Let's go back and see if we can handle this dragon from the beginning. This dragon is still gonna be maybe harder than any geometry problem you'll ever see, but I wanna show you that we can tackle these really hard problems if we have incorporated some of those takeaways into our attack. Let's go ahead and give you another 2 minutes on this one. All right, that's been a little over a minute. All right, that's been just about 2 minutes. I hope that we weren't actually trying to solve this. I mean, yeah, technically it is solvable, like the textbook way. We don't have, we're not being graded on how well we align with the textbook methods, right? So we should have some of these other tricks up our sleeve. I want to know an answer choice you eliminated and the reason why you eliminated it. Everyone try to find an answer choice that you really don't think can be the right answer and tell me why. Okay, so John, I think you're right to be suspicious there. Doesn't have the same structure. Interesting. So he's saying C doesn't have the same structure. Yeah, like notably, John, in C, what's missing that you think should be there? Yeah, like, again, so we're trying to look at this strange area. It is strange. But that area is outlined by both a rectangle and a circle. So there's gonna have to be some circle-ness to our answer. And the signal for circle stuff is pi. This does not have a pi in it. And so I think that's gonna be problematic. Yeah. I think C is gonna be wrong. Well, I mean, I know C is wrong. I would see it as being very suspicious because it's lacking circle stuff. And this problem clearly depends on the circles, right? So the fact that it doesn't have pi's means it's a huge red flag. Cool. Any other answer choices we can eliminate? Well, D also doesn't have pi, right? It has the markers for 30, 60, 90 triangle stuff and 45, 45, 90 triangle stuff, and no pi stuff. So this one also seems kind of suspicious to me, right? I should have pi because I'm definitely dealing with circles here. Go ahead and mark that as an outlier. Cool. Of the three that remain, let's go take a look at E. I think E is going to be the easiest to try to estimate. So Jay asked a good question. How do I know that the pi's aren't going to cancel out? Pi's will cancel out when you divide by pi's, I believe, more commonly. So, like, let's go, actually, you know what, this is worth doing. Let's go take a look at the previous problem. All right, because we came up with answer D here. Answer D was correct. But note, answer D doesn't have pi in it, and it doesn't have root 3 in it. That's because we started with information about pi and root 3 in it. And then when we incorporated the pi stuff from the circle and the root 3 stuff from the triangle, it did cancel out. Jay, you're right, it is a ratio. But the divisor, right, the denominator, doesn't have anything to do with the circle. So let's go take a look at it. I mean, this is a tough problem, okay? I will solve this problem for real for you as well, so you can see. But if you wanted to think about, like, generally how you would solve this problem, right? It's kind of like that triangle area we did. Like, don't actually solve for this area. Find the area of all the other stuff and take it away from the rectangle, okay? And so that would involve something that looks like this. Rectangle area minus some weird circle stuff. And so what we should end up having here is, you know, minus some pi stuff, right? The only way you would get rid of the pies is if you then added circle stuff, right? So that they would cancel out. You subtract circle stuff and add circle stuff in a way that perfectly cancels out. That's not going to happen here because we're definitely dealing with a curvature as a boundary, okay? And that curvature, that area that's shaded has curves and the area of the whole thing does not, right? So you should have something with pi in it. And if you are dividing by something, that would not have pi in it, all right? Because pi is not part of the entire area, but it is playing a role in the shaded area. Okay, so you're not going to add back circle stuff in equal amounts here, so you're definitely going to subtract some circle stuff from it, and then that's going to leave you with the pi. Yeah, so I feel pretty confident it's not going to cancel out. All right, so C's out, D's out, we need some pi stuff. Let's take a look at E. Root 3, all right, well root 3 was 1.73-ish. Pi over 2, well that's like 3.14 over 2. What is this going to be? That's going to be less than 1.6. All right, 3.2 divided by 2 would be 1.6. So this looks like 1.73 minus 1.57. That's about this. 0.16 is like a sixth. Does it look like a sixth of the area is shaded? No, a sixth of the area would be an entire block, right? A sixth of the area would be something like this. That's clearly not the two shaded pieces. So I get rid of E. So now you're left with A and B. And these are both really ugly to tackle. Let's take a look at A. All right, A, 3.14 minus 4 over 12. Well, that denominator is going to be negative, right? So negative divided by 12 is still negative, okay? And I'm subtracting something. Let's take a look at what you're subtracting. 3 root 3, we actually did that on the previous problem. 3 root 3 is about 5. 6 minus about 5 is about 1. 1 divided by something positive is positive. So what we've got here is a negative minus a positive. Answer A is going to be below 0. And that only leaves answer B. Answer B is weird. Okay, I'll just say answer B looks really, really weird. It's strange. Where's the root 3 business coming from? Because like Jay, I think you're very right to be suspicious. Like, I mean, maybe the pi's would cancel out or something like that. Where is root 3 coming from here? Anyone have an answer for me? How is root 3? I thought root 3 doesn't have to do with circles. Root 3 had to do with like 30, 60, 90 triangles. Yeah, it's actually related to one of those bullet points we had earlier. The corner triangles, the overlap. Yeah, remember when we said when you have multiple shapes, how those shapes touch or overlap is really important. So I'm going to go ahead and blow this picture up, and I'm actually going to zoom in on this top middle box. This guy. Take a look at how these circles touch, this area right here. This line I'm drawing, that's a radius from the center circle, or the circle on the left. This is a radius from the circle on the right, and this is a joint radius between the two circles. Radii are equal. And so the triangle that is formed is an equilateral triangle, and that is the point at the bottom of the shaded area. So there is some triangle stuff happening here. So the way that you could do this the textbook way, and I don't think I would ever do this the textbook way, I would also say that this problem would be extremely rare to see on an exam like this because of how difficult it is. But what we can do here is say, hey, this is 60 degrees, and that means this is 30 degrees. That means this part here is actually a fraction of the circle. 30 degrees is a 1/12 of 360. This is a 1/12 of the circle right here. That means this one is as well over here. And this is an equilateral triangle where the side length is the radius. You can figure out the area of this 12th circle if you just set the radius as r. This would be pi r squared over 12. So would this. And if this is r here, you can use your side ratios to figure out the rest of the dimensions of the equilateral triangle. I'll just go ahead and tell you the equilateral triangle's angle would be r squared root 3 over 4. If you subtract this and this and this from the area of the box, which is r squared, you'll get r squared minus 2 pi r squared over 12, and then minus r squared rad 3 over 4. That'll give you the area in terms of r of this weird shape. You would divide that by 3r squared because the top half of the shape had 3 of these r squared boxes. And that will give you answer B. That is too much work, okay? That is too much work. So we want to think back to our takeaways. And when we see these hideous answer choices, we want an additional way to solve. You're on notice, right? You have circles. You're going to need some pi stuff. Get rid of C and D. Then I would estimate, right? If we know these ratios, or if we know these irrational numbers, we can be in good shape. E says this is about 16%. That's too much. A is negative. That's impossible. And by process of elimination, we have answer B. If you estimate answer B or you actually solve this out, this is just under 1.5% of the overall area is shaded. But again, we're not actually interested in getting the specific answer. We're interested in getting 4 wrong answers here and moving on without totally destroying our brains. So that one's pretty brutal. If you kind of like this problem, the other, or if you actually want to solve, the other type of problem that's kind of like this is to create a square and then like draw 4 quarters of circles like this. It's going to be pretty bad drawing. Oh yeah, really bad. Draw the 4 quarters of circles like this and figure out the area of the overlap there. That could be an interesting problem. I would say, I think Faye asked it earlier, like, yeah, you can do this with advanced math, and you could do this with advanced math too, but you also can do it with just knowing special right triangle angles and areas of circles and squares. Whew, all right, that was pretty brutal. That was a tough lesson. I'll be just straight up honest with you. That one was hard. But hopefully we're leaving with some decent takeaways to then throw at challenging geometry problems in the future. Remember, don't assume, infer. Don't assume, infer. Know the special shapes where you can derive one measurement from any other, okay? Whenever you have multiple shapes in a geometry problem, you really want to consider how they touch or where they overlap, all right? That's going to be critical information. If you have been given the description of a shape, draw it from scratch. If you've been presented a shape on the screen, redraw it. And we talked about ways to use the yellow pad as ways to draw more accurately. Right, finding tough areas, we're actually going to get rid of the other areas. It's kind of like solving for interesting probabilities, right? Sometimes you want to solve for the opposite probability and subtract it from 1. Same thing here. Recognizing when to use these types of numbers, when they're appropriate, and how to estimate them. And then, yeah, estimating in general, when you don't want to do all the rough calculations. Take a look at the answers, and if they're spread apart enough, use those to your advantage. Cool. I think we'll call it there. We'll call it there. You get a calculator, an on-screen calculator for the integrated reasoning section. You do not get one for the quant section. Yes, you will not be able to rely on a calculator for the quant section. Do not plan on that. So something very drastic would have to change. Yeah. John, do you have a question? I mean, that's good. Oh my gosh, that was a big question. That's a lot of text. Hold on. Someone just sent me a document. I'll read that in a minute. That's right, John. Good resources for problem sets. Yeah, the problem sets, like besides the official guide. Like if you don't have the official guide, you need it. My official guide is sitting. No, I don't know where it is. Probably downstairs. Yeah. So how do you create problem sets out of the official guide? I mean, you can do that. Like just pick some random problems and do them. When you have the practice exams, the official practice exams, those come with an online question bank, and you can build sets from there. That's an option. And if you get exam packs, you know, the other exam packs, official exam packs, those come with more questions. But yeah, I would just say, you know, you can do them out of the book. All right, good question. How does one get better at guessing and moving on, in my view? You have to be very honest with yourself when the problem has you beat. Yeah, so Jay, it's a mindset thing. You have to understand that the GMAT is going to be hard. It's hard for me. It's hard for everybody. And that knowing that the test is going to be hard and knowing that the problem is going to beat you on a few of these is like the first step to success. Remember, it's like those problems that you struggle with so much, they're actually, I think, worth the least. So they're really just there to tempt you and waste your time. And, you know, a minute through a problem, if you are just like spinning your wheels and not going anywhere, that's the sign that you should move on, right? If you're going to get a problem wrong in 5 minutes, you might as well get it wrong in 5 seconds and save the remaining 4 minutes and 55 seconds. So it's discipline. Yeah, I would just give yourself like, you know, a handful of free passes, right? Guilt-free passes on the exam. I mean, it's up to you to determine how many, but I would give yourself maybe at least 4 in the quant section and 4 in the verbal. Like I have free, Jeff's given me license to totally just bail on questions 4 times on each section and not feel bad. I think it's actually a good move, right? That's probably what we need to remember is moving on from a really hard problem instead of wasting time on is actually a net win. And so maybe that's what you need to convince yourself it's a good idea to bail. Yeah. Yeah, I mean, I've seen people miss like 8 to 10 problems on quant and get a 49 or 50. Like, which is a very strong score. Yeah, you have to miss, you have to, like, you miss the hard problems and there you're saving time to make sure you're getting all the ones that you should get, right? So if you're gonna get like a 49 on quant, like you don't really need to get the ones that are super hard. You don't need to get the 51 level quant problems, but you do need to get like just about all the 45 level quant problems. The problem is if you waste all your time on the 51 level quant problems, then you won't have enough time to make sure you're getting the 45 level quant problem right. And now like we've kind of missed on both ends. So yeah. Gui, I'm going to have a hard time responding to that now. Yeah, so he actually just said he missed 6 spaced problems on quant, got a 50 on a GMAT prep exam. Yeah, you can miss like a handful of problems and do really well. Again, that's kind of the nature of adaptive testing. Like it's going to be hard. You're going to miss some problems. We want to make sure that when we miss a problem, it deserves to beat us, right? It deserves to beat us. And if it deserves to beat you, maybe it would have been wiser to let it go after less than a minute.